Hello and welcome to Bitcoin Explained, where I break down some of the more complex and technical aspects of Bitcoin in a simple way. In this video, we'll be talking about elliptic curves, which is one of the key building blocks behind the cryptography that Bitcoin uses. This is actually the second video in a 5-part series on the cryptography behind Bitcoin. In video number 1, we talked about finite fields, another key building block behind the cryptography that Bitcoin uses. If you haven't watched video number 1, I highly recommend going back and checking out that video before watching this video. And it's absolutely required that you would have watched both of these videos before moving on, because everything after this builds on the foundation of finite fields and elliptic curves and how those two come together to allow us to do things like elliptic curve cryptography and a lot of the other magic behind Bitcoin. With all that said, let's talk about elliptic curves. To explain what elliptic curves are and how they work, I will be sharing my screen. I've created a Jupyter notebook here. This just allows me to put a little bit of text in with a lot of visualizations, because I think the best way to understand elliptic curves is to visualize them as much as possible. I'm a very visual learner, and I think visually is the best way to explain this topic. The way this video is structured, we will first be looking at what elliptic curves actually are. Then we'll move on to points on elliptic curves and what groups are. Then we'll talk about elliptic curves and straight lines, how they intersect and why that's important. We'll talk about how point addition works, and then finally the key operation, which is point multiplication. All right, let's get started. So what actually are elliptic curves? Elliptic curves are basically just curves that have a certain form or equation. The equation will always have this form here. You've got y squared on the left hand side and x cubed plus ax plus b on the right hand side. In this case, a and b are just constants that define the shape of the curve. And if we take an example with a equal -1 and b equals 1, then the curve will just look like this here. If we change the constants a and b, we will just get different shapes of the curves, as I've done below here. You can see in this case, I'm keeping b constant as 1, and I'm changing a from -3 all the way to 0. So for -3, it looks like this. It's actually a disjoint curve, so you've got two parts to the elliptic curve here. For -2, you've got the same thing. The two parts just move a little bit closer. -1 is actually the same curve that we looked at above. This is just displayed a little bit smaller. And then for 0, it looks like this. So you can see with changing a and b, you just get different shapes of the curves. One thing that all of these curves have in common, though, is that they're symmetrical about the x-axis, sorry. This is due to the y squared on the left-hand side of the equation. Now, let's move on to points on the elliptic curve. So a point on an elliptic curve is just an xy pair that satisfies the given equation for that elliptic curve. So if we look at the same curve that we looked at in the very first plot with a equals -1 and b equals 1, then we can see that the point 3, 5, if you look at the x-axis labels here 3, y-axis labels 5, and you can see, based on the visualization, this point does actually lie on the curve. We can even plug in the numbers and verify this mathematically. So on the left-hand side, we would plug in 5 for y, 5 squared is equal to 25, and then on the right-hand side, we would plug in 3 for x. So first we would have 3 cubed, which is 27, minus 3 is 24, plus 1 is 25, and 25 does in fact equals 25. Why do we care about points on an elliptic curve? So the first reason is that we want to define an operation that we can do based on points on the elliptic curve. But the second reason actually is that if we think about the elliptic curve not as a continuous plot on a graph like we see here, but we think about it as an infinite set of points that just satisfy the elliptic curve equation, the one that we see up here, then it allows us to look at elliptic curves as a group, and therefore we can apply the rules of a group to elliptic curves, which allows us to do some really cool abstract math. Now, for those of you that have never done abstract mathematics before, this will be a new concept. I'm assuming this will be most of you. And for those of you that have done it already, you will have probably heard about groups, and this will just be a revision. But I'll quickly talk about what groups are, and then we'll define what the key mathematical operation on elliptic curves, point addition, actually is and how it works. Okay, let's look at groups. So, as is stated here, a group is just a set of elements equipped with a single binary operation that satisfy the following key properties. Now, the first property here is just the binary operation, and then after point 2 we get to the actual properties. So, a binary operation is basically just an operation that combines two elements in a group to produce another element that's also in the group. Now, this sounds a bit abstract because this is abstract math, but let's go back and look at this point up here. What that basically means is that if we look at the points on the curve as the elements in the set, then what that means is that if we combine 2 points on the curve, which are part of this group of an infinite number of points, then we should get another point on the curve because it has to be an element in the same group. That's basically what this means. Now, the first property that this has to satisfy is closure. Closure is very much related to what we just said. It just means that if you do the binary operation between two elements in the group A and B, now star here just denotes the binary operation, then you get another element that's also in the group. Associativity means that the operation must be associative. So if you do the binary operation on 3 elements and you do it on A and B first, and then take the result of that binary operation and do a binary operation between that result and C, then you should get the same as first doing the binary operation on B and C, then taking that result and doing the binary operation between A and that result. The identity, that just means that there must be an element in the group such that if you combine that element with another element in the group, that element remains unchanged. This is really similar to how in normal math for addition you have the number 0. So if you take any number, let's take 5 for example, and you add the identity element 0 to it, that leaves the number unchanged. So 5 plus 0 is just 5. This is called the identity element here and works very similarly. You'll understand how this works and what it is in a couple minutes. Then the last property is the inverse element. So what this means is that for every element A in the group, there must be another element called B here, also in the group, such that if you combine A and B, you actually get this identity element that we talked about in property 4 here. Then in that case, element B is called the inverse of A. Now let's go back to the example of using the number 5. Remember that if you add the identity element 0 to 5, 5 remains unchanged. Now in this case, the inverse element of 5, which would be the additive inverse, so to say, of the number 5, would be minus 5. Because if you add 5 and minus 5, you get 0, which was the identity element for addition that we introduced. The concept of this is basically directly translatable onto groups here. It just works a little bit differently, but the logic is really the same. So yeah, that's basically what groups are. Now, before we move on to point addition, I think one thing to highlight here is that this might seem abstract to a lot of you, and it is abstract math, but one of the beautiful things and the amazing benefits of doing abstract math and abstract algebra is that we can define the binary operation in any way as long as it fulfills all of these properties here. So we can define the binary operation to do an operation on the elements in any way possible as long as when we do that operation it follows all of these principles here. This is really, really cool because it allows us to create our own definitions for operations, which is exactly what we do for point addition. So yeah, let's look at point addition. So as we talked about previously, point addition is just when we combine 2 points on the curve and get a third point also on the curve. Now, the way that point addition is defined relies on some key observations about elliptic curves that might seem a bit unintuitive at first, but I'll show you a lot of visualizations that will prove this to you and will make you understand why they're important as well. So the key observations are that if you have the elliptic curve in a coordinate system plotted on a graph, and you also plot a straight line on the same graph, then that line will intersect the elliptic curve at either 1 point or at 3 points, except in just a handful of special cases. This will always be the case unless you're talking about these special cases. And another key observation is that as long as we don't pick a perfectly vertical line, so a line that goes straight up and down perfectly, and we intersect the elliptic curve at 2 points with the straight line, then it's guaranteed that we will intersect the elliptic curve at a 3rd point. Now this is very, very important for point addition. Let's look at the 3 different scenarios. So 3 intersections, 1 intersection, and a vertical line, and then we'll talk about how point addition actually works. So to prove that there will be a lot of cases where there's 3 intersections, I've created this elliptic curve here, which is just x cubed plus 8, and then a straight line 0.8x plus 2.4. Now, it's very easy to see that this line intersects the elliptic curve at 3 points, which is here, here, and here, but I've kind of created this straight line in a way where this would be the case within the given range of x and y values for this coordinate system. One other thing that we could do now is we could say, okay, this line obviously intersects 3 times, but what if we had a similar straight line and the same elliptic curve, but the straight line has a way steeper slope, so that this blue line goes up almost vertically, but not exactly vertically? How do we know that it would ever intersect this red line here another time? Because just looking at this range of x and y values, that might not seem too obvious, which is exactly what I've done here. So if we create a way steeper straight line, 10x in this case, on this limited range within the coordinate system, you might think that this blue line never intersects the red line again. But if you zoom out far enough, which I do down here, you see that the blue line at some point actually does intersect with the red elliptic curve again. This roughly happens at the coordinates 100 and 1000, as you can see up here. Now, what's really interesting is that this will always happen, no matter how steep this straight line is, as long as it's not perfectly vertical, at some point it will intersect the elliptic curve again. Mathematically, we can actually explain this. I won't spend too much time on this, but basically what you have to do in order to be able to compare the 2 equations is take the square root of the elliptic curve equation, which in this case would look like this. But one thing that you can see is that as we go further along the x-axis here and increase the x value, this term here will be completely dominated by the x cubed, which is the case for any form of an elliptic curve. So at some point, as x approaches some limit, this will basically just be x cubed, or the square root of x cubed, which is roughly equal to x to the power of 1.5. Now, mathematically, this is guaranteed to at some point rise faster than any straight line that we can choose that isn't a perfectly vertical line. Let's talk about the second case, which is 1 intersection. Now, if we use the same elliptic curve, but we create another straight line, which basically is just a little bit less steep and shifted up on the y-axis a little bit, it looks like this. Now, does this one ever intersect again? If we zoom out, we can see that it actually never intersects again, which makes a lot of sense, because for the same reasoning that we had above, because this line crosses over here, but it doesn't touch the U-shape anywhere here, we know that as x increases, the red line will start to rise faster and faster, or steeper and steeper, And because this is a straight line, this will never get steeper, so they're mathematically guaranteed to never cross again as x increases, and as x decreases, the elliptic curve does a U-turn basically here anyway. So yeah, the line never intersects again. Now, one intersection is important for understanding elliptic curves and how they interact with straight lines, but for the binary operation that we want to define, point addition, they're actually kind of irrelevant, because by definition, in order to have point addition, you need to have at least 2 points that you can add together, and a straight line that only crosses at 1 point doesn't seem too relevant for that case, which is exactly what's the case. So it's good to know this, but this won't be too relevant for what we will talk about later. Now, there's another obvious case for one intersection, which is just a perfectly horizontal line. Again, same reasoning, we don't have to spend too much time on this. Then there's another special case, which is vertical lines. Now, we can either have a vertical line that touches the curve somewhere that's not at the perfect middle of the U shape, or the U-turn of the curve here. In that case, what will happen is the straight line will only ever intersect the elliptic curve at 2 points. We'll talk about why that's relevant in a few minutes. And then the other vertical line, which is perfectly tangent to the elliptic curve at the U shape here, and that's another special case. Now, what happens if we have a tangent line like this, but the line is not perfectly vertical? In that case, it might look something like this here. Now, in this scenario, if we have a tangent line, a line that's perfectly tangent to the curve at some point, and it's not perfectly vertical, the same reasoning applies that we used above, where if a straight line intersects an elliptic curve at 2 points, and it's not a perfectly vertical line, then it's mathematically guaranteed to intersect a 3rd time. The same reasoning applies here. So if we have a straight line that's tangent to the elliptic curve, but not perfectly vertical, that means that it's mathematically guaranteed to once again intersect the elliptic curve at a 3rd point, for exactly the same reason, because at some point, if you increase the x value enough, the elliptic curve line will have a steeper slope than the straight line, no matter how steep the straight line is, as long as it's not perfectly vertical. Now, this is really important because it allows us to define point addition in a second. Now, before we move on to point addition, let's actually look at what the inverse of an elliptic curve point is. We've introduced it above, and the fact that it's relevant for 2 of the conditions, but just to define it. So the inverse of an elliptic curve point, so if we have the point P here, is just always the point if you reflect this point over the x-axis. So it'll have the same x-coordinate, but it'll just have the negative of the y-coordinate. So for the point 3, 5, which you can see 3, 5 here, the inverse element is just 3 minus 5. So the inverse of any point is always just the point reflected over the x-axis. Okay. Now, how point addition actually works. So there's 3 different scenarios that we need to cover to explain how point addition actually works. So we can either have 2 points that are different and not on a vertical line. We can have 2 points that are on a vertical line, or one of them is the identity element. And we can have the case where the 2 points are actually the same, so you're adding a point to itself. Now let's look at the first scenario. You have 2 different points and they're not on a vertical line. Now the general logic for point addition of elliptic curve elements will always be the following. So first, if you have 2 points, in this case we're adding A and B, you draw a straight line through the 2 points being added together, and then you find the point where this straight line intersects a 3rd time, and then you reflect over the x-axis. So if you add A and B, on this elliptic curve together, then you draw a straight line through A and B, find this point C where it intersects again, and again remember, because this is a straight line that's not perfectly vertical and it intersects at 2 points, we know that it's mathematically guaranteed to intersect at a third point. In this case, this point's really close to B. We find this point and then we basically find the inverse element because we reflect over the x-axis to get the result of A plus B. Now, this might seem a bit unintuitive, and it was a bit confusing to me in the beginning as well. I was like, why do we do this reflection over the x-axis? It actually turns out that there's a mathematical explanation for this, but there's also a more intuitive explanation, which is that we need to reflect over the x-axis for associativity. So remember that associativity means that first doing A plus B and then adding C should give the same result as first doing B plus C and adding that to A. Now let's actually choose 3 points A, B and C and do these two operations, or I guess 2 operations on one side and 2 operations on the other side, and see that they actually end up at the same point, but only because we do the reflection over the x-axis. So if we have a different elliptic curve and the following points A and B, if we do A plus B, once again we find the straight line that goes through A and B, find the point where it intersects for a third time and reflect over the x-axis. A plus B is down here. Now if we then take another point C and add that to A plus B, so the result that we got from the previous addition, then again we draw the straight line, find the third point where this straight line intersects, which is down here, and reflect over the x-axis. So the result of first doing A plus B and then adding C will actually be up here. Now let's do it the other way around. Let's first do B plus C. Now you can see they're exactly the same point, so B is still the point from here and C is still the point from here. We draw the straight line through them, find the third point where this line intersects the elliptic curve and reflect over the x-axis, so B plus C is down here. Now if we take the same point A that we had above and add B plus C to A, then what we do is we take the straight line through them, find the point where it intersects for a third time and reflect over the x-axis. And as you can see, this point here, which is B plus C first and then adding A, is the same as doing A plus B first and then doing plus C. Okay. Now, some of you might wonder, how do we actually find this third point? Basically, this goes back to some formulas to compute the slope from pre-algebra. You might still remember this. I won't go into too much detail, but basically if you have 2 points, then you can compute the slope like this, and then you can compute the x and y coordinates of the third point by just plugging the values into these formulas here. Let's look at the second scenario, which is where we have points on a vertical line or the identity element. So thus far we've only talked about what the inverse of a point on an elliptic curve is, which is just the point reflected over the x-axis, in which case those 2 points actually lie on a vertical line. But we haven't talked about what the identity element actually is. So to recap, there were 2 properties of a group where the identity element came into play. The first one was the identity property, which just stated that if you add the identity element to a point on the curve, then that point remains unchanged. Now I've translated that onto points on elliptic curves, but that's what this property just means. And then the inverse element, meaning that if you have an element in a group, in our case a point on a curve, and you add the inverse element to that element, then you get the identity element. In this case, that means if we have a point on a curve and we add to it the inverse of that point, which is just the point reflected over the x-axis, then we get the identity element. We'll talk about this in a second. In elliptic curve point addition, the identity element actually has a name, and it's officially called the point at infinity. Now, this term is a bit confusing, and infinity is in general a confusing concept, and I prefer to refer to this point more as the point that is nowhere. Now, this point isn't technically on the curve, and therefore it wouldn't belong to the group, but remember that in abstract mathematics we can define binary operations however we like over groups that we can also arbitrarily define, as long as those definitions are consistent with the rules of a group. So in this case, the group is then defined as all of the points that satisfy the elliptic curve equation, as we already mentioned, plus one extra point, which is this point at infinity. By having this extra element, the point at infinity or the point that is nowhere in this group, it just makes all of these properties actually work out and satisfy all of these properties. Thinking of this element as the point that is nowhere also makes property 4, for me at least, a little bit easier to understand, because if you combine a point on the curve with a point that is nowhere, then nothing changes. So yeah, let's recap quickly the inverse element. Sorry, this is lagging a little bit. The inverse element, again, if you have a point P here, then the inverse element is just the point reflected over the x-axis, as we said. Adding a point to its inverse. Now, if you add a point to its inverse, then you would again draw the straight line that goes through the 2 points. Now, in this case, this is a perfectly vertical line. So that just means that if you draw a straight line through a point in its inverse, which means adding the 2 points together, then you will get this straight line that just goes into infinity without ever touching the elliptic curve again. And that's why we have this point at infinity, or the point that is nowhere, because this line will touch the elliptic curve again nowhere, in a way. That's a way to think about it. It's a bit abstract, but we just need this point at infinity to satisfy all of the group properties and to make all of the arithmetic on elliptic curves and for point addition actually, yeah, to get it to work. Yeah. Then we'll talk about the last scenario, which is adding a point to itself. Now, this will be a really key operation because it will then allow us to define point multiplication, and later on in this video series, it'll actually help us understand how we get from a private key to a public key. So it's really vital to understand this operation to ultimately at some point be able to understand how a private key actually gets converted into a public key and how it's done in a really safe way. Okay, adding a point to itself. So adding a point to itself can be thought of sort of as bringing 2 points infinitesimally close to each other until they become the same point. At that point, the slope of the line intersecting those 2 points will just lie tangent to the curve, and therefore adding a point to itself can be done simply by taking the derivative of the elliptic curve at that point, and then getting the point where this tangent line at that point intersects the curve again. So basically, you can, if you add 2 points that are the same point, it's kind of like you still put a straight line at that point. And as we talked about previously, as long as this straight line is not perfectly vertical, it's mathematically guaranteed to intersect a 3rd time, or in this case a 2nd time, depending on how you want to look at it. And then we reflect over the x-axis again and get 2a down here. So if we add the point a to itself, the result will be down here. Now, one interesting thing that I've done as well that I quickly want to introduce here is I've created a Python class that handles elliptic curve points and also point addition of elliptic curve points. And the way that it can be used is that if we actually define this point here as the point -1, 1, which is this point A, then we can just do point plus point, and we'll get 3 minus 5, which corresponds to the correct coordinates, as you can see in the visualization here. If we were to add a to itself another time, it's the same as doing a plus 2a to get 3a. Then we would again do the same mathematical operation. We would draw the straight line through a and 2a, find the point where this straight line intersects the curve a third time, reflect over the x-axis, and 3a would be up here. Now, visualizing this a repeated number of times is a bit cumbersome, but the Python class that I created can actually handle this very easily. So if we were to, instead of add the point a to itself twice, which gets us 3a, we could do that 7 times as well to get to 8a, and the result of that would be the x-coordinate minus 1.3 roughly, and y-coordinate minus 0.1 roughly. If you do this a repeated number of times, you can actually get something that in elliptic curves we call point multiplication. So adding a point on an elliptic curve to itself a given number of times is referred to as point multiplication or scalar multiplication. Now the term multiplication is a bit misleading here because the operation is still just point addition done a given number of times, but that's what it's called. So it's important for you to understand what this is. So for example, above we saw that if we add the point with coordinates minus 1, 1 on that elliptic curve that we had up here. Now here I call this point P, but up here it was called A, it's the same thing. To itself 8 times, then we get these coordinates here. Doing it for a small number like 7 is pretty easy like this, but what if we wanted to do it billions or trillions or even more times? This would become really cumbersome. There's a really neat mathematical trick that you can do here, which is that if you want to compute 8a or 8p, we'll just refer to it as 8p from now on. What you can do is you can first compute 2p and then add 2p to itself to get 4p, and then add 4p to itself to get 8p. So instead of having to do 7 additions, as you can see in the code down here, you actually only have to do 3 additions and you still get to the same point. Now, for 7 additions, this is, you speed it up by dropping 4 additions. Doesn't seem like that big of a deal, but if you wanted to compute 1000p, for example, the way that you could do it is you could compute 512p, 256p, 128p, 64p, 32p, and 8p. Now, the interesting thing about this is if you've already got 8p, then you only need to add that to itself once to get 16p, add that to itself again to get 32, and then you just start adding it to itself and saving all of the intermediate results to actually get 1000p. And instead of having to do 999 additions, by doing it this way, you actually only have to add p to itself 9 times to get 512, and then if you add the other additions that you have to do to then add all of the other intermediate results to it, you end up with a total of 14 additions rather than 999, and this scales astronomically as you take the number of addition or point multiplication that you want to do to larger and larger numbers. In computer science terms, this means that we go from having a big O of n operation to a big O log 2 of n operation, which means that we can do point multiplication with really, really large scalars, like talking trillions and higher orders of magnitude, really efficiently and in milliseconds. Okay, so to summarize, we've seen what elliptic curves are and how they behave. We've seen how point addition works, plotting a line through the 2 points, find the point where it intersects again, reflect over the x-axis. We've seen that elliptic curve point addition is associative. We've also understood what the identity element is, the point at infinity or the point that is nowhere. We've seen that every point on the elliptic curve has an inverse, and we've seen that we can do point multiplication really, really efficiently. Now, this is all that you need to know about elliptic curves. I hope that this video was clear to you. If you have any questions, feel free to ask them in the comments, and I'll be sure to answer all of them. I'll see you in the next video.